Good morning, good evening, and welcome to our final day 3 of the ASBU ABU WorldDAB technical workshop webinar series for 2026. Thank you for your interest, and we hope you will find today's presentations useful. Today we turn to the technical aspects of DAB Plus networks, and we have some very interesting presentations from our panel of experts. First, some housekeeping on the Q&A. Q&A box is at the bottom. Please enter your Q&A questions into the box, and we will attempt to answer them in the Q&A session at the end of the presentations. All questions are good and encouraged. And even if we don't have time, we will still answer the questions, and they will be published along with the videos next week. The actual presentations will be available as we present. So they're all day 1 and 2 are already available. Okay, that's great. Now, first up, I'm going to give a quick update on network design, the basics, before we launch into more details and some excellent examples from Hans Wolter. So let me share my screen and we will start the day's proceedings. Okay, hopefully you can see my screen okay.
Yep.
Something not right here. Excuse my apologies. I thought I had it set up properly. Okay, let's move on. So we're going to go over some use cases for SFN and MFN, look at design constraints for both, and have a few final remarks there. So let's get straight into it and look at multi-frequency networks, or MFN. This is the case where you have different content in each coverage area and different frequencies in each coverage area. For single frequency networks, however, we have the same content in each coverage area and we use the same frequency. And that allows DAB to be very spectrum efficient over wide area networks, which require multiple transmissions. So they're the two types of networks of transmitters. So here's an example of an MFN. This is taken from New South Wales in Australia. And what we see here is a lot of polygons in different colors. And each one of these blocks, these polygons, represents a license area to be covered and the frequency that it is used. So you'll see that the colors define the allotted frequency blocks, and a number of those are the same. So you can see a number of yellow, a number of orange, a number of blue frequency blocks. Each color is the same frequency. So in this case, the transmissions need to cover the license area, but must not interfere with the transmission in those other license areas, whether co-channeled or whether they're adjacent channel. So let's look at the design constraints now. We know we operate in VHF band 3. We're operating at a multi-frequency network. The critical constraints, in this case, the coverage area needs to be the same as the license area, and generally must cover a specified percentage of the coverage area and or the population in that defined coverage area. And we've got what we can't do as well, must not provide coverage outside its licensed area. That would then be overlapping and provide a service where it is not licensed, so that's not allowed. usually that's a regulated requirement. Must not cause co-channel interference, CCI, into adjacent license areas using the same frequency block. So in that previous picture, the ones with the same colors. And must not cause adjacent channel interference into adjacent license areas on different frequency blocks with their N-1, plus or minus 1, plus or minus 2, or so forth. So we've got two different constraints there. Now, we have lots of planning support through ETSI and ITU standards, but I will also bring your attention to the EBU guidelines, EBU Tech 3391, which is commonly used as the baseline standard. So now let's move on to the details here. For the co-channel interference case, we can see on the left-hand side of the screen, we have the wanted DAB signal. And in this case, we have a protection ratio, co-channel protection ratio of 12 dB as per Tech 3391. So the unwanted co-channel signal must be 12 dB or more below the wanted signal. And this is particularly on the edge of the license area. For the ACI case, what we see is that the wanted signal in the dark green, in this case, the adjacent signal can actually be higher than the wanted signal. And that's because it's protected by frequency masks in the receiver. And N plus and minus 1 protection ratio is minus 40 dB. So it's 40 dB above the wanted signal. And N plus or minus 2 and higher is 45 dB. So that gives a lot of license, you might say, to designers in terms of using adjacent channels, which is very useful in the design process. So the co-channel protection ratio defines a minimum distance between different transmissions on the same frequency block. And in particular, I've gone too far. I know, sorry, I'm getting myself confused. So, yeah, minimum distance between these different transmissions on the same frequency block here. So we can see here you've got coverage A and B. And the unwanted interfering DAB service is some distance away. Now, I'm using a minimum field strength coverage for the mobile outdoor case, reception mode, and it's 50 dB microvolts per meter. And that's what we use in Australia. In other countries, it's a different value because different parameters are used in defining the minimum required field strength for the different operating modes. Excuse me. So what does that mean? Well, what is the maximum allowable interference field strength? And generally taken to be at the edge of the license area. So we can calculate that. The maximum allowable interference field strength is determined as the unwanted value. Unwanted field strength must be less than or equal the wanted field strength minus the protection ratio, which is 12 dB, minus the location correction margin. And we calculate that location correction margin with the formula we have here, where sigma is the location variation standard deviation, and mu is the distribution factor for mobile reception at 99%, which is 2.33. And if you calculate that, it turns into 13.2 dB. So what we're saying then is that if we do those calculations, considering that minimum field strength of 50 dB microvolts, nominally at the edge of the license area, and we take the PR and the location correction margin, the maximum interfering field strength is 24.8 dB microvolts per meter. So basically 25 dB less. So that's a useful thing to know. So we'll come to some So that's how the design of the networks needs to be taken into account. You can't have signal overlapping from an adjacent co-channel out from a different license area into your license area, which is more than that value, that 24.5 dB microvolts. Moving to single frequency network coverage, same thing, VHF band 3. In this case, the critical constraints is the CCI between single frequency networks have the same PR constraints as the multi-frequency networks, okay? And the ACI is the same constraints as multi-frequency network. But within SFNs, there are strict timing requirements. Again, these are all defined in the standards documents. So let's have a bit closer look at that, because DAB uses OFDM. It is for its modulation, and it has a guard interval of 246 microseconds, which is a nominal distance between transmitters of 73.8 kilometers. But that's nominal, and we'll look at that in more detail in a moment. If you look in 3391, you'll see this diagram, and what it says is it defines the useful component and the interfering areas. Generally, what I've found in the design is we don't worry about that 246 to 350 microseconds. If you're outside the 246 microsecond guard interval, you're classified as an interferer. So let's look at an example, because actually what we're really looking at is taking into account the time of arrival difference. What we have is this dependency on the results in the transmitters in the single frequency network having variable powers, and we need to address their specific local constraints. So the time of arrival is defined as the absolute difference, absolute value of the time delay between the receiver and the transmitter of transmitter 1 and transmitter 2. So remember, this is a single frequency network. Both signals are on the same frequency. So we need to look at the time delay between at the receiver, time of arrival difference. And that's related to the distance between the receiver and the transmitter in both cases. And we note that the time of arrival difference should not exceed that guard interval if the field strength difference is less than the co-channel protection ratio plus the location correction margin. And we can see an example here. And here I've actually put an intersite distance, not at the minimum of 73, but at 90 kilometers. And I'm saying TX1 is 10 kilowatts, TX2 is 1 kilowatt. So the danger of self-interference is when the field strength difference is less than the co-channel protection margin and location correction margin. And we only need to deal with it in the Australian scenario if the field strength, the wanted field strength, is above 50 dB microvolts per meter. So in this example, even though the transmitters are more than 73.8 kilometers, there is no actual interference between the transmitters. But what we find is because one transmitter is quite high and the rate of decay decreases as in field strength decreases with distance, there's potential for interference actually on the other side of transmitter 2. Transmitter 1 being on the left side of the graph, transmitter 2 being the peak in the middle of the graph. And this little line with, you can see SFN danger, including the location correction margin, is on the other side of the transmitter. So what I'm trying to highlight here is it doesn't always happen. The interference is not always in between the transmitters. It can be the other side of the transmitters as well. So just some final remarks here. So MFNs are used to deliver different content using different frequency blocks. Single frequency networks deliver the same content using the same single frequency block over wide areas. SFNs are often used within multi-frequency networks. That's very standard. During design, care needs to be taken to respect the varying nature of the field strength coverage due to the terrain and building clutter. Sometimes there's a mountain range between two transmitters, for example, that will make a difference. MFN design is focused on protection ratios for co-channel and adjacent channel interference. Single frequency networks have the added constraint of time of arrival differences between multiple transmitters. So during design, we must take into account propagation variations and the impact of terrain, clutter, and water paths and atmospheric conditions as well. So thank you for that. We now move on to Hans Wolter. Hans is the CTO at DAB Italia and responsible for a lot of the design work within DAB Italia's vast DAB network in Italy. So I'll now hand over to Hans to present his presentation on the practicalities of single frequency network design. So over to you, please, Hans. Thank you.
Thank you very much, Les. Thank you for your excellent presentation. You have covered really a lot of very interesting stuff. And let me just continue in the direction. So Les has really launched the basics for single frequency networks and MFN networks. And I will go a little bit further and discuss a little bit about resilience inside these networks, because SFN has some very interesting options. First of all, please let me introduce a little bit our company. DAB Italia is a national DAB network operator. We have a license for the whole country of Italy. Our company is actually owned by commercial radio bands, which are also active in FM. So basically in Italy, DAB is funded by FM operators. We also have additional capacity, and therefore we have also external customers. We still have capacity available. So if you're interested in broadcasting in Italy, give me a call. And we do a lot of stuff. So we own the multiplexers. Therefore, we gather all the content from our customers and owners. We do the multiplexing, we do the distribution, and we do the broadcasting, of course, of all of this. So we also own the transmitters and the antenna systems in most of the cases. There are some scenarios, of course, where we share sites with other operators. But basically, we do our network planning from our perspective, and this has proven the best solution, let's say. It has been very cost effective and efficient. Also, of course, we do some research and development. We have been active in this DAB world since, I think, 1996, 1997. So nearly 30 years in DAB. We did tests in the past on DAB Classic. We moved, of course, to DAB Plus as soon as DAB Plus was actually available in the encoders, and we have been the first ones to run DAB Plus encoders in Europe. We also are implementing SRT for the EEDI distribution. We have been the first to implement this, which is very efficient protection technology to allow, let's say, EDI distribution on not so reliable IP networks. In Italy, IP networks are not always 100% reliable. With this technology, we have excellent results, and we are very happy over this, of course. We also do some lobbying activities at the political level, and we do, of course, also some marketing campaigns through the national DAB platform, which is digitalradio.it. Everybody knows Italy. It's this strange thing, which is very interesting. I'll come back to that in a second, because Italian territory has a lot of specific characteristics. So there are some very large flat areas, but we also have high mountains. And most of the central part of Italy is very hilly. We have big islands, we have small islands, and we have, of course, also very high mountains just next to the sea. So it's always a very mixed scenario, basically. And we have a very, very long coastline because we have the Adriatic Sea on one side. I just go back. You can see here you have the Adriatic Sea, you have the Ionian Sea, and you have the Tyrrhenian Sea on the other side. It's a very long coastline, and this has also some reflections. And we have, therefore, also a lot of neighbors, at least 14 countries, which we have to coordinate with. So let's say the frequency usage for DAB in Italy has a lot of constraints due to all these neighbors. On the right side, you see the current frequency layout for our multiplex. Due to all these neighboring countries, it's not possible to have a single frequency network at national level. So basically, we have two very big areas. One is the yellow one, which we run on 7D, and the other one is this light blue, greenish one, which we run on channel 10D. And then we have on the borders a few other areas with different frequencies. But let's say the big SFN areas are this one on the Tyrrhenian side and on the Adriatic side. And this creates, you can see this on the left side, a lot of SFN issues, which Les has already covered very well, due to the big distances we have to cover here. And the areas here, for example, where you see basically the arrows exceed the famous 73.8 kilometers. So we have to put into place a lot of strategies to mitigate SFN interference, especially on the self-interference part. Okay, so, but I'm not here to speak about self-interference, but on resilience. Just let me go back one slide, sorry. Because SFN has this fantastic capability to make your transmission networks more resilient. When you run a DAB network, you have, of course, especially in SFN, you have some issues and some risks you have to manage, of course. And you have interference issues, so self-interference and external interference, and this has been covered by Les. Self-interference, of course, inside the SFN. External interference can be code-channel interference, so, or of course, interference from adjacent countries coming over the sea. And over the Mediterranean Sea, we see propagation effects which are incredible. So we receive stations from Spain, from Africa. So there are some risks. And of course, when you run your DAB network, you have to manage the signal generation, the multiplexing, the signal distribution, and TX operation and tower operation. And in this context, when we talk about resilience, we will just look into the last two options. So the transmitter operation and the tower operation, which are, of course, intrinsically connected. So just to put things a little bit clear, what is redundancy? What is resilience? Redundancy is, of course, when you add the layers of protection through hardware. So you have N+1 transmitters, you diversify, for example, the signal distribution, and I think Christian will touch this later on. You can have redundant antenna systems, you can have double sites or, let's say, double towers. Resilience, of course, is this is a definition, just is the system's ability to continue operating in the event of a failure of one or more components. And in this case, this means basically when you have a single frequency network with overlapping coverage areas. When you look at redundancy, it's very difficult to implement, especially, let's say for us, for example, we are a commercial operator. We have a limited budget. We cannot afford to have a double satellite distribution, a double IP distribution. We cannot build radio links through all Italy. Currently, we are running 280 DAB transmitter sites, and we have to accept some risks, and we have to try to mitigate them. We cannot afford to have the double number of transmitters, the double number of antennas, and so on. And therefore, we are now considering this resilience approach. Probably some of you remember at the beginning of DAB, we had this nice schemas which were very much like a cellular network. You had one transmitter coverage area, another transmitter coverage area, and so on. And in some cases, and we did the same when we started, basically we planned our network, one transmitter, and then we tried to cover the adjacent area and so on. So the first idea was really to do a lot of coverage and not so much resilience. Because in Italy, the first thing we tried to do is really to cover the highways. Because radio listening in Italy is mostly in cars. We have about 76% of radio consumption in cars. And so we really looked a lot at road coverage, so at large area coverages. But when we finished the first thing, we realized that we didn't build the network, which was on 2 slides earlier, but we got something like this. Why? Because, of course, transmitter site selection is not so easy. You have to find the right sites. You have to optimize the costs, etc. So at a certain point, our network was much more like this. And this means that in a lot of areas, we had more than one signal arriving. And we realized that, for example, when we had a transmitter failure, we didn't get a lot of complaints because actually there was another transmitter already on air on the back. And then we proceeded and we developed our network more and more. And we arrived to something which was where we had maybe one big site because we have high mountains, which have a big coverage area. We had a smaller site, which has maybe an urban area or a smaller hill or a smaller tower, and so on. So our network was starting to look like something like this. This is, of course, a schema. It's not the real thing. And there, in this case, you have some areas where you have one coverage, a few areas where we have 2 coverages, and some areas where you have even more coverages. And this really works out really well. And I show you now a real life situation. In Italy, we have, let's say, the capital of Italy is Rome. It's a very big city. It's very extensive. It has also a difficult territory because it's a hilly terrain. So you cannot just put one transmitter into operation and hope everything will work. And it's very extensive. And basically, we have 3 transmitter sites which serve the area of Rome. The first one is Monte Cosce, which is on the north of Rome. It's pretty far away, but it's a big transmitter. We have Monte Mario, which is really in the center of Rome. And we have Guadagnolo, which is on the east side of the city, and which is also a very big transmitter site. You see on the top left the field strength measured and planned, of course, for these transmitters. In Italy, as you can see, we plan for mobile coverage as a basic level, And also we refer to the EBU Tech 3391 document. And basically, this says we are looking for 43 dB microvolt at 1.5 meters, which is a realistic car reception scenario. And this gives us a coverage area for the different transmitters, which you can see in this table here. So Guadagnolo, which is the biggest transmitter, will cover over 4 million people just by this site. Montecosce 3.3 million and Montemario 3.3 million also. In the city of Rome, these two transmitters, let's say for the urban area of Rome, this means that they will cover about 2.7 or 2.6, 2.7 million people each. Because of course, as you can see in the slide before, the coverage areas also extend outside of the area of Rome. But in Rome, they cover, let's say, all three, most of the population, at least for mobile coverage, of course. And what does this mean? This means that if you have all three transmitters running together, you have a coverage like this. You have a coverage, a population coverage of basically 96.8% of the Roman area. As you can see here down in Italy, we don't have a very significant obligations for coverage. So within 5 years of license awarding, you have to cover at least 70% of the population. We cover in Italy at national level around 91% of the population at this point. However, of course, in an urban area like Rome, it's very important to have a coverage which is really significant. Basically, the only areas where you don't have coverage are here, this area here, where you have a coverage, but let's say it's under the planned value. So it's under 43 dB microvolt. Probably the car will work anyway, because what we see is that cars currently work with about 35 dB microvolt at 1.5 meters, but we do not consider this area covered. But now the interesting part, what happens if one of these three transmitters fails? So let's say if we have all three transmitters on air, we have a 96.8% population coverage. If, for example, the transmitter Montemario fails, the one in the center of Rome, you still have a 96.1 population coverage, and which is basically a 0.7% difference, which is really very small. So most of the users will really not notice anything in this case. Similarly, if we have Montecosce, the transmitter which we had on the north side fails, we still have a 96.6% of coverage. So only 0.2% less population coverage. So still the difference will be really low. And even if Guadagnolo, which is of course the most influent transmitter, fails, we still be over 95% of the population coverage. So let's say in the practical context, differences will not be noted so much. And this brings us to really an economic consideration for Rome, where, for example, I have two scenarios basically, a resilience scenario and a redundancy scenario. I have divided the costs in capital expenses, where you have the cost of transmitters, antennas, filters, cables, and installation. And then you have the operational costs, which are rent, maintenance, and electricity. And of course, let's say if you have a resilient scenario, like we run currently, for example, we are facing costs which are more or less in this order. Of course, these are not the precise costs, but they are, let's say, pretty reasonable and pretty aligned to real life costs we are seeing in Italy for sites of this kind, which are pretty important, let's say. Montecosce and Guadagnolo have very big antenna systems, and Monte Mario is in the center of Rome, so it's an expensive site by itself because it's in a very strategic location. Anyway, if you look at the redundant scenario, of course, the cost for the transmitters is more than double because, of course, you have also to add the cost of the logic, the switching, and all this stuff. In this case, I have not considered a double antenna system, but of course, you have more a complexer situation because you have to connect two transmitters to the same antenna system. So you have a switching mechanism. Installation is more complex, etc. You will have to pay, of course, more rent because you will occupy more space. You will it will require, let's say, it has a higher value. So usually the rent will be higher. Maintenance costs will be a little bit higher because, of course, you have more hardware to check. And of course, also electricity costs will be higher because even if one of the redundant transmitters will be in standby, it will still be switched on, so it will consume power. It will require more cooling, etc. And therefore, you can see that there is really a significant difference in the cost of running such a system. Of course, this is a specific example, but it is quite significant, especially if then you have to scale this up to a national network. So I'm not saying that in strategic sites you should not think about redundancy, but that probably you can, in some cases, skip over redundancy and think about resilience because it will allow you to lower the costs. Last slide, basically. So I think we should be pretty on time, Les. Resilience is already included in your single frequency network. So it's not something you have to add, or it's a function or an option. So it's really a free feature of DAB. You don't need specific hardware. You don't have to pay a fee. So use it. And what we really can say is plan for it. Because, for example, when we started, we didn't plan for it. We discovered this functionality basically on the road, because when we started 20 years ago, this didn't exist as a thought. When you choose transmitter sites, of course, plan maybe for a little bit denser network with overlapping areas. And if you plan for an urban area, plan for something which I call a Mercedes star layout. You have the Mercedes star on the right top. So if you can have 3 transmitters around the city, you will probably get a very resilient network. You will have to pay for 3 sites, but you can maybe skip on some redundancy aspects in this case, because if one of these will go off air, you will have time to restore the functionality, and most people will not note any difference. Also, if you have such a layout, of course, you will also have a better indoor coverage, because if you go into a city from 3 different sites, you will have a higher probability to do indoor, because it's probable the probability to get through a window in a building is much higher. So an additional reason for having more transmitters around the city is really the indoor coverage. And it's not about field strength, but it's really about the probability to go into the buildings. When you choose antenna systems, go for open patterns. So what we've seen is to have very simple systems, like the one here above with dipoles, etc. Usually spread the signal far and uniform around the coverage area. And this will allow you really to manage your resilient network, your overlapping areas. Because when you go for directive systems like this one, which we have, of course, because sometimes you have to protect your SFN or something else, you're not making full use of this feature. So if you can, go for open systems. Of course, this might also create some problems in your single frequency network for your synchronization. But in this case, really, I suggest to review the transmitter site choice. Try to find alternative sites because really it's better to have open antenna systems, open coverage areas instead of very directive systems. In the end, it will work much better. That's at least our experience. And so I hope this has been useful and interesting. And if you have any questions, I think we have a Q&A at the end. And otherwise, you can contact me later on. Let me just close the connection and back to you, Les. Thank you very much for this opportunity.
Thanks, Hans. Thank you for your insights and your extensive experience in this. And it's actually a really good point that actually you don't actually need to do redundancy up front, especially when you're establishing new networks. You're better to actually having more sites and use that to provide resilience rather than make the individual sites super robust and redundant. So that's a very, very good piece of advice. And also the use of antenna patterns within single frequency networks, using those open patterns, as you call them, more omnidirectional where possible. That helps that resilience as well. So fantastic, very useful advice. Okay, thank you. We're going to move on now to talk about emergency warning systems, and in particular, how Germany is integrating the automatic safety alert into its public warning system. We have Speaker Carsten Sorger from the Digital Radio Bureau Deutschland. So, Carsten, please share your screen as you're doing, and over to you. Thank you.
Thank you very much, Liz, and I'm so happy to be able to give you an update on what ASA is doing in Germany, because we are really on track there. So just like a teaser for what's coming up in the next 20 minutes, we here in Germany for ASA, we have our key stakeholders aligned. There's a network and the rollout is on track. We have broadcast capacity units reserved for ASA. We even have, and we are very thankful for that, we have ASA certified radios available in the markets to buy online or in the retail stores. I'm responsible of a PR launch and communications, which will start in September. We talk to the national and federal emergency agencies, and all in all, we believe, as DAB Plus started in Germany in 2011, this now with ASA is the biggest technology boost since it starts in 2011. Now, let me go into a few details. This was the reason why we started with ASA. 5 years ago, in the summer, we had a flood claiming 180 people's lives. This was tremendous. We never had that since World War II. And everything was flooded. No electricity, no mobile phones, no DSL network connection, nothing. No trains, no roads, nothing. And the rest of the communications took happened via radio. So there, of course, there was a high power principle, and this was the last resort. People, like in Spain when FM was the last resort, the people were listening to the radio. So we just started 5 years ago thinking of how can we make a radio part of a resilient emergency warning system. These are players and partners in our association. You might have seen few of these logos. Some of them you might know, some of them you might not know. But what does that mean? In this association, all working together for ASA, we have broadcasters, both public and private. We have network providers, Christian with Media Broadcast, for example, but others as well, on a regional and national level. We have regulators, regional and national level, and we do have the state authorities on a national level. And we talk, of course, to Fraunhofer, who are the engineers and do all the muxing and writing programs. So this is a circular approach, 360 degrees. We talk to everyone, and everyone is included. For the case you might not know what ASA does, it's an emergency warning system, and it has 6 certain features. The first feature, the alert, you might know from FM radio. It's a spoken announcement. Of course we have that. It's a radio. But the next 5 features are ASA only. Number 2, geofencing. The warning area is transmitted, which is important because countries are big, and floods or whatever happens, big catastrophes, they are regional. So it's always good to have a geofencing, a location code with it. And once you have the location code, it would be great if you could wake up radios at night, because in the R Valley, I just have shown you the picture of the flooding. The R Valley flood happened at night. The people died during the night because there were no sirens, there was nothing. If they only had been able to wake up people with the radio. So we built in wake-up function into ASA. We have synchronization, which means that the radio every minute looks, is there any message coming or isn't? Because it saves battery power. We don't keep them online all the time. They just seek for messages a few seconds within a minute. We have a switchover function, which is called Other Ensemble Alert. If a MUX you're listening to, a program on a MUX you're listening to is not having any ASA messages, the radio still can be pointed towards another program which relays the warning message. And number 6 is not that important, but you have it. It's dismissed. If you heard a message and it's being repeated, you can dismiss that, and you're all set. This is our logo, ASA, Automatic Safety Alert. This is not a marketing logo. This is a certification, because this is meant to deal with lives of people. So we certify radios. And we have started the scheme together with WorldDAB and Digital Deutschland. And we now have on the German market about 35 different models from a handful of manufacturers available to buy. We have on our website www.dabplus.de/ASA, we have a listing of the current models available to be bought in Germany, and they are based on a test scheme, which I'll talk about in a minute. And this, of course, now with the service coming in a minute, it's like a circle. We have now the service, we have the radio, we'll be on air with it very soon. This is a listing of the tested end products by DTG London, which is neutral, and you might know them from the digital radio tick mark. So we put the ASA testing on top of the digital radio tick mark testing. So if you were to buy an ASA certified radio, you can be sure that it is a standard piece of equipment. It is being tested against the strongest and the best current standard. So we would recommend everyone, if they buy a radio, if you buy a new DAB radio, look for the ASA logo, because this is the latest and the most modern test. In order to wake up radios, you need a location code, and you have to go to a website to find that. And this is international. Wherever that be, Australia or Kuala Lumpur or somewhere else, you can go to that website. It's called www.asa.radio. I've put it on the right-hand side there. And it's in 4 languages. It's in German, because we start in Germany, English, French, and Spanish. And if your country is looking towards ASA, we would be happy to integrate your language at a later time. So you type in your address with house number and zip code, and then it has this 12-digit location code. And the location code is basically 1 square kilometer. Now you might ask yourself, how come that this is a rectangle here in Berlin? Well, the world is a ball, a round shaped, so it's still 1 kilometer in diameter, but it's just, how maps are being displayed if they are laid flat. We are looking towards regular service of ASA in Germany, and I talk about this in a very, very few seconds, but we have been testing the service on testing occasions separately many times before. And what we do as there's hardware available, there are 35 different models to be bought in Germany. We have a continuous ASA test in Germany. We call it the Eiffel Tower location code test. Well, you see the picture. Everybody loves France. Everybody loves Paris. And with testing location codes, obviously we had to choose one which is outside of Germany. And as everybody loves France, we just decided, okay, let's take the Eiffel Tower in Paris. And what is happening is if you have in Germany a radio that's ASA capable and you type in the Eiffel Tower location code, you have a continuous test every 5 minutes. What is happening, it will wake up your radio from standby. Remember R Valley at the night, wake up radio from standby, tune to a program, let the program run 30 seconds and then go back to standby again. So if you have a capable radio, you can test this in all of Germany. Once you're in Germany, you have access to DAB+, you can test this with the Eiffel Tower location code. Now we're getting into more detail regarding implementation of ASA in Germany. We are being German and people talk and people write, so we came up with an ASA guideline. It's about 50 pages. And it'll be available in English in the fall. Now it's German only. And we have 3 certain focus points. So first of all, for the German market, these guidelines have a common understanding of ASA about the terms and the processes and technology. Of course, the guidelines also define technical requirements and responsibilities. Who does what and when. And in the end of the day, these guidelines support the implementation and rollout of ASA in Germany. And as you might remember, we have a strong federal state system with 16 independent federal state and local states. And of course, then they have the government of Germany, which is all of Germany. So we have regional governments like in Italy that are very strong. So we have to look at this as well in the guidelines. When do we use ASA? We decided from the start that we are using ASA for the highest priority warnings. What does that mean? This is legal German. I translated it into English, so I hope you bear with me. States of tension and defense, which is obvious, which is war. It's disaster scenarios, which is floods. Significant threats to public safety, which is terrorist attacks. Official emergency announcements in civil protection. For example, this could be like a toxic cloud coming from somewhere going to somewhere else. And everything is being done and carried out only by authorized bodies at the national, state or federal level. So it's not the fire department of some city doing this. This is only by authorized bodies. This is very important for ASA because it's activating so many radios. And we have a national security and safety agency, which is called BBK, and they operate the MOVAS system. I come to MOVAS through this abbreviation in a second. It means Modular Warning System. Once you do MOVAS via radio, you have 2 choices. You can do a live announcement from the studio with a host or speaker, just as in with FM, or you can choose to do an automated text-to-speech variation. We chose text-to-speech in Germany, which I think is the best choice. For example, it is available 24/7. Many commercial stations are not available with live people during 24/7, and only a few public broadcasters still do it. So it's, text-to-speech is available around the clock. Text-to-speech also, because it's automated, means emergency messages are being broadcast quickly. You are on the air within a minute. And this is important. Be on the air within a minute. And you can, of course, what I talked about this earlier, reference to another MUX, which is OE, other ensemble reference. And the fun part of it, well, fun in quotation marks, you can do this automatic system via broadcaster, because I work for a broadcaster, or network operator. And we work together with Media Broadcast. This is Christian's company. And we work together, and we decided to ask them to do ASA for us on the network operator perspective. I was talking about MOVAs, and I would like to give you a very short glimpse of the system. You have seen this in your country as well. On the left-hand side, you have the sources, the different stations where you might have some emergencies being pointed to. On the right-hand side, you have the warning multipliers and the warning channels. For example, cell broadcast. Cell broadcast is wonderful. The mobile phone starts with a text message and an alarm sound. It's also with a location code, and it goes to the smartphones. We, of course, have sirens and a regular radio or other emergency services. And down there, you see in green, we included now ASA-capable DAB receivers as warning channels, and, of course, the radio stations or, of course, the network providers as warning multipliers. This is probably the most important slide now for this day. This is our transition into regular operations. 6 steps I would like to point out. First of all, I work for the national broadcaster, which is called Deutschlandradio, and we are on the national broadcaster, and we are allocating CUs for this TTS service. We call the service ASA-DE, DE for Deutschland, Germany. So it's a national channel, and it's a 32 kilobit per second. And the warning messages and location information will be provided by the MOVA system of the BBK at the national or federal level, as just explained in the slide before. Then our colleagues at the network provider Media Broadcast, they are automatically will convert the data into spoken messages with ASA location code. This is like a formula. And number 4, they use a text-to-speech engine, and they use a local one, because using a local text-to-speech engine is always a good idea if the network is down, if the internet is down. Sampling and muxing will be done locally by network provider Media Broadcast, and then, of course, they'll be broadcasted nationally with the national service ASA-DE. As we are national public broadcaster, this service is being financed by the public radio fee in general, and we know that commercial radio will follow in their own time and respect, and we talk to them and they are integrated, but they will start at a later date. Number 6 is important. One more time, ASA is a separate TTS channel. ASA is not part of a regular programming. It's not part of a music or news program. It's a dedicated service running independently from regular programming, because this is an easy way to have local messages all over Germany being transmitted with location code and activating only the radios that are meant to be activated, as not to interrupt regular music and speech programming on a daily basis. So number 6 is also very important. Now I'm almost finished, but I will show you a video now. I'll explain before you what we will see. You will see a video of 2 radios. One is having a test location code, which is active. So one of the 2 radios will activate from standby, as we would have loved to have it in the Ahr Valley when the flood came. This one will demonstrate that radios can be woken up with a location code from standby, for one. And you will see another radio which will remain silent. And this radio, you'll see a little picture above the radio, has a location code which is just 1 kilometer next to the active location code, just 1 kilometer apart. This is how detailed ASA is working. And then, of course, a signal starts, and then a text-to-speech engine plays a little message. This is a warning message, and then the radio will sleep again. I will now try to roll my video. At the first few seconds, it'll be silent because you will see the ASA marker blinking, and then the radio turns on, and then you'll have sound, and I hope it'll work fine. So I start my video now.
Amtliche Gefahrendurchsage für Deutschland. In Deutschland findet heute der Warntag 2025 mit einer bundesweiten Probewarnung statt. Es besteht keine Gefahr für die Bevölkerung. Es besteht kein Handlungsbedarf. Berichten Sie über Ihre Erfahrungen gerne unter warntag-umfrage.de. Sie hörten eine amtliche Gefahrendurchsage von Bundesamt für Bevölkerungsschutz und Katastrophenhilfe.
So once again, this video was to demonstrate two things. For one, there is a location code. And secondly, we can wake up radios from standby with a correct location code. This is the true big thing about ASA, these two items. This is my last slide. We're looking back at the time frame. We have started with the ETSI started in 24. We protected the trademark in 25. We have been testing ASA on a regular basis on warning days. We started with the workshops and the groups. We talked every 6 weeks. We have regular meetings. They wrote the guidelines. And now the technical introduction working group is come to its end basically. And in September 26, we'll start with the regular services on air. And now the whole system from the radio to the broadcast to the TTS will be available in Germany. And we'd be happy to share at a later date how everything went and how well the system works. So thank you very much, and I'm looking forward to your questions.
Thank you, Carsten. That was really enlightening. I think you're certainly world leading in terms of integration of digital radio into emergency warning systems. As you pointed out, low tower cellular systems often fail in examples like the floods in Germany, even if they have cell broadcast. So it's a very important wide area warning system. The other thing that I really liked was the fact you've got all your stakeholders together. This is so critical throughout the lifetime from start to finish of DAB. And also that the public service broadcaster is leading the way in this particular aspect. And then the commercials will come too. So again, another great example. So good stuff. I hope that's been enlightening to our audience today. Now we're going to move over to more about reliability. In this case, reliability of DAB plus distribution networks. No distribution, no signal. We have Christian Werner, Senior Product Manager at Media Broadcaster in Germany, to talk about this topic. So thank you, Christian. Please share your screen. Over to you.
Yeah, thank you very much. Great to be with you. I'm Christian, Senior Product Manager at Media Broadcast in Germany, and mainly responsible for the development of DAB+. We just heard about ASA from Carsten, and that fits quite well also to my topic, as you will need for a safety alert system, also a reliable distribution network, of course. But just allow me to say a couple of words to Media Broadcast. Media Broadcast, the largest service provider in the broadcast and media industry in Germany, and we consider ourselves as the backbone of the media, from contribution to distribution, which fits also to my topic today. We create platforms for the media, we realize major projects, we promote networks and solutions, and our focus is squarely on digital terrestrials, mainly DVB-T2 HD, and of course DAB+, some of the most important products in our company. Well, at the end, we also consider ourselves as pioneers in the development of other applications such as 5G. A few numbers from our country and our operating systems. We are working with about 550 employees. 250 of them are in the field service, and they are all together guaranteeing those high availabilities which are so typical for the broadcast industry. Of course, 24 hours the day, 7 days per week. We are situated with them, our colleagues, at 70 locations all over Germany. And sorry, Media Broadcast is a Freenet corporation company. Well, what I said, we create coverage for radio every time, every day, in every moment. So what makes a DAB Plus network reliable? I think 6 points you have to say. You need a proven, stable technology and established methods. You need redundancies. You need the power and environmental resilience. You need to check your transmissions. You need to have good monitoring. And of course, you need to have a good field service with efficient logistics behind. Now, what is the currency we are working with if we are talking about reliable networks? We are offering service level agreements to our customers, and we have here 99 to 99.5% of availability, which is a very low standard. I think you will not find it in Germany anymore, but it would mean 361 to 360 days of availability of your network. A medium standard would be 99.6 to 99.7%, so 363 days availability. And the standard you most often will find in Germany is 99.7 to 99.8% of availability, which means 363 to 364 days of availability. So if you put on the radio button, radio is there. Everything above that is quite high standard and of course more expensive, 99.8%, or if you want to reach the big aim, the big 5 nines, 99.999%, where you are just allowed to have a downtime of 3.5 seconds. Now, the efficiency gain of time is somehow marginal, as you can see, and it is expensive. It depends on how much you invest in the single components, but you see a single minute of downtime can result in thousands or even millions of euros in lost advertising revenue, missing regulatory compliances, or severe damages to your brand. So coming to the operational availability for DAB+, proven stable technology and established methods. What you are seeing is a very simplified view on the production line of DAB+. So you are starting with creating the signal, in this example, an audio signal, which it's a case. Normally, you can also use data transmissions, of course, and you then send your audio signal to the contribution lines, and via those lines, you come to the head end, which is the heart of the total production, I would say, from DAB+. Here at the head end is where the product DAB+ starts. So if you buy in Germany DAB+, you buy the product starting at the head end. Everything before on the left side is independent on the market, and then you can buy your lines such as you are fine with it. So now on the head end, after a lot of coding and decodings, etc., you send your audio signal to the distribution networks, where it goes unchanged to the sides and then to the transmitters, which are at the antenna sides, and via the antenna to the receivers. With that construction, depending on which components you are using, you can easily guarantee 99.5% of availability, I guess. And well, I mean, here is no open source or something like that included. There are some network operators having some trials with it, but I think for established networks, it's too risky to use such things. Well, here you would add to increase your availability, a redundancy, which at the end means backup system. Keywords here could be, for example, geo redundancy. We in Germany, we are using for our multiplexers at Media Broadcast 4 different head ends, and we are using them, or we have installed them on 2 different locations so that you are safe from weather conditions or from other hazards, let's say. On the transmitter side, for example, you could implement a 1+1 redundancy configuration, which means that you have 2 real transmitters at every side, which is quite an expensive solution. You could just use driver backups or dual drivers, what would be more economic. At the antenna side, I think Hans mentioned it already, you can choose different configurations. You have the possibility to use a construction that allows you to drive the antenna in a half antenna mode, let's say. So it's quite expensive solution, but it would guarantee a signal at the end of the production line. So generally, all this redundancy concept follows a master and slave concept. The next step to strengthen the network availability is to invest in the power and environmental resilience. For example, you can run on each production step fuel-driven generators, or maybe, if cheaper, depends on the local situation, a battery emergency supply system. You can also construct 2 different feeding points of power at the sides or at the head end side. For example, it has happened quite often that in a construction, a digger cut off the terrestrial signals. So choosing a second feeding point could avoid that issue. Much cheaper than that are other components in the production line which avoid voltage fluctuations for a time of 1 to 5 seconds, so that the power supply is not interrupted. I think in English would be UPS, the word behind. So another measure I've shown before is the way of your transmissions. You can use a different physical way in your transmission, not only using terrestrial connections, but also satellite capacities for your contribution and or distribution. It could be a supplement which easily brings you up to 99.8% and plus and more for your network. I come to that in a minute later. Last but not least, you need a good network operating team with a strong monitoring and a good communication to all affected parties, of course, to the customer, and a fast and highly skilled field service with an efficient logistics system behind. And I guess that would be all for your 99+9 network. The costs are depending on how many sites you are operating. In Germany, we have 2 national multiplexes. The first national one, which is the big flagship, has around about 190 transmitters, and we are close to that, what I'm here showing, but this means an investment of several millions of euros. So, as we have run out a little bit of time, a short digression on the contribution and or distribution lines. I've shown before 4 examples. There are, of course, very much more. By the way, in my experience, the most common failure in cause in the networks, the failure cause is here in the contribution and distribution lines to find. Well, everything is on EDI. I'm not sure. I think we do not use any more EDI. So you can, on one hand, in first example, back up your audio signal. The PAD and NPADs are going via FTP. And you can use, for example, 2 dedicated network line to transport your audio signal. A dedicated line is a private, high capacity and exclusive telecommunication line used solely to transport your audio, or if you want video feeds also, with a guaranteed bandwidth. You can alternatively make your backup line via the internet. That should be more, that should be cheaper. And you can use also in the 4th example, instead of the internet, a mobile solution using LTE, for example. The last thing would be a solid one audio signal transferred via the dedicated network line to the head end. Well, coming to further contribution, distribution, the picture I've shown before, satellite capacities. Satellite capacities, in Germany, we use them for the national multiplexes. The public broadcasters for their networks use it also. It depends on the cost and on the quantity of your sites in your multiplex. In local regional multiplexes, the fixed cost absorption has not that effect like in bigger networks. Yeah, if you're running, as I said, 190 transmitters, then it makes a lot of sense also to use satellite capacities. By the way, you reach via satellite stations which are in the countryside and difficult located, let's say. So in Euro and Germany, we are using 4 major positions for our satellite capacities. We have Astra 23.5 degrees east, Astra 19.2 degrees east, or Eutelsat 8 degrees west and 7 degrees east. I think the public broadcasters are using Eutelsat. You can use, of course, other capacities, also, for example, Starlinks or something like that. So we have the expertise you need for your projects. If you would like to know more about it, feel free to get in touch with me. So let me thank you for your attention.
Thank you very much, Christian. That's very comprehensive presentation there. I think what it really shows to the audience is that there are a lot of different ways to deliver, and you can use multiple ways at the same time to provide that extra resilience. But of course, the higher availability, the higher the cost. So
Yes.
For new players and greenfield people, you can gradually build those layers of reliability over time as you build your listener base. In Germany, of course, there's a very large listener base for quite a while now. So it's become an essential service and the availability and reliability must also go along with that. So very good. Thank you very much. Okay, this is good. We're up to Q&A time. We've got multiple questions here, which we're trying to answer in about 10 minutes, which we probably won't do. I'm going to read out a couple of questions and ask some of our panelists to answer them. So the first one is actually a question from yesterday. It's from Meiza Yin, sorry. And this is for Alex Kurz. And it goes, how about geocoding? What's that for? I would like to ask Gates here if we would like to change DAB+. Are there any simulcast transmitter for AM and DAB? How do we plan to establish head-ending DAB features which need to be added for car importing to Myanmar? So that's great to see Myanmar's interested. What rule guidelines do we need to enact? And finally, do we need frequency planning for our country? Well, there's about 5 or 6 questions in there. I think the big thing I would say, I would recommend you go to the Establishing DAB Plus Digital Radio ebook in the first instance. That covers a lot of those things. But I go over to Alex now for a quick question, maybe more focused on the transmission side of things. So over to you, Alex.
Thank you very much. Good morning, good evening to the audience. Regarding simulcast delivery of medium wave AM signals and DAB signals, that is not available because the frequencies that are used are in the hundreds of kilohertz versus the hundreds of megahertz. So there is no transmitter available, to my knowledge, that does simulcast delivery for those two technologies. The other question, especially about the cars, our recommendation would be to look at European Union or several Middle East country regulations, for example, Saudi Arabia and UAE. All of them have implemented rules that new cars that being imported into the country must have DAB inside. Take a look at the various regulations that are published there. And to the last part of the question, frequency planning, yes, this is highly recommended, just like you do frequency planning for digital TV or for FM radio. And of course, besides coverage planning or frequency planning, you will also need to do regulatory coordination with your neighboring countries to be compliant with ITU rules. With that, there is a question about head-end. I would deflect this to my colleagues from the head-end manufacturing side. With that, back to you, Les.
Thanks very much, Alex. That's a good point. Remember, you can always contact our presenters through the project office, and you can establish a one-to-one dialogue with them through that process. And we encourage that, absolutely encourage that. We've got a couple of questions from Lofi Chalali. I'll direct these to Hans. So first question is, could you please explain how it is possible to implement a large nationwide SFN network, such as the one you presented in yellow for Italy, while at the same time complying with the rule that the distance between DAB transmitters operating in an SFN should not exceed 73 kilometers?
Okay, thanks for the question. Just as a first note, the rule does not say that the distance between transmitters must not exceed 73 kilometers. It's only a question of setting the right offsets on the transmitter. So basically, if all your transmitters are within 73.8 kilometers, you don't need to set any offsets, and you will be fine and not have any self-interference. What we do, for example, during the planning process is we make a lot of simulations to verify the propagation times of the transmitters already on the planning part. And of course, if you have a high tower site, this becomes very delicate. But there are some mitigation techniques, which I have presented actually last year here in the seminar. And I will try to put up the slide from last year. Let me see if I can do this on the fly. Can you see this? Yes, I guess so.
Yep, we can see that.
So I had a number of slides on how to mitigate self-interference. And so there are a few rules which are really thumb rules. And one is, of course, if possible, avoid sites which are very high because they will propagate far away. Avoid high powers if
where we've lost looks like we've lost Hans is there. Hans, are you still there?
Too much in contrast with the high tower, high power sites.
Okay. All right. I think they got a little interrupted, but anyway, we'll continue.
Yeah, I got
we
back.
have a,
yeah.
You seem to be having an intermittent. Oh, here we go. You've got an.
Yeah. Okay.
Continuing.
So, as I said, use low height sites, medium power, simple antenna systems. And then there are a few tricks. And one is the procession, which I call. And this is something, if you remember the map of Italy, where you have a long coastline, basically I start on the top transmitter, which has no offset. And then going down to the south, the offset, of course, increases, and the antenna systems are more or less directional that they go south. So I expect from transmitter 3 not to go back to coverage area of transmitter 1. And I expect transmitter 4 not to go back to the coverage area of transmitter 2. And so the delays basically add up over time, of course, over time. And this is one technique which we use. Basically, if you go look at the Adriatic Sea, you will have in the north transmitters which have an offset of 0, and in the south you have transmitters which have maybe an offset of nearly 1 millisecond, so 1,000 microseconds. Another way, of course, is this one here, and then I finish it. If you have one transmitter with a very, very big coverage area, you can, of course, under this umbrella, set up a number of smaller transmitters inside this coverage area. This is, of course, also a possibility. This does not address the 73-kilometer problem, but it's a way to build SFN coverages, of course. I hope this helps a little bit. And Les, you told me there was another question.
Yes, it's also from Lofi. Could you please explain the following? In a DAB plus SFN network consisting of one high power site and several low power sites, should the time launch delay of the pilot site, I assume that means the main site, be set to 0 microseconds, while appropriate time launch delay values then applied to the other sites? I think you've basically answered that, but you might want to add to it.
Yeah, so this is something you can really work out already on the planning phase with the softwares available. So I suggest first to plot the coverage area of the big site in order to understand what actually the coverage area is and how it relates to the coverage areas of the smaller sites. And then you can really choose the right offset. Let's say if the transmitter is 90 kilometers away, maybe you can choose something like 50, 60 microseconds as offset. But this really depends on how the coverage of the smaller sites is. So you have to do this really carefully on the planning. It's not something which you can just decide looking at the transmitter sites. You have to really to do this in a planning process.
Okay, that's good. That's good. All right, we've got a couple of extra questions. I just think we might just push through and get a couple. For Carsten, there was a question. There's two questions regarding ASA in cars, which you've already typed the answer. But I think the general audience might like to see those or like you to answer that directly. So, what's going on with ASA in cars?
Well, to begin with, in 24, we had the standard, the ETSI standard regarding the domestic receivers. And this is the base ground for what we do now in the fall when we start with the system and the service. But we have been talking to car manufacturers and they would love to have ASA in cars. So we're talking to the chair of the technical committee and to WorldDAB members and to other parties. And we believe we can prepare that kind of discussions and the implementation of that together with car manufacturers within the next year. So we are looking towards implementation of that now after we started the service in Germany.
Yeah, absolutely. That's a good answer. Yeah, I understand it's much more complicated in cars because they move and there are other factors to be taken into account as well. And there's actually a task force within the technical committee addressing this at the moment. So it's a high priority, and as DAB does, as WorldDAB does, it's always moving with the times and finding solutions to those problems that keep popping up. So thank you, Carsten. Okay, I've got a question now for Christian. It is, are you using a common site for all contributions for the whole country? Is this more economical than sending programs directly to transmission head-ends?
Well, we are not using just one site. We are operating several networks, let's say. That depends on the MAX you are connecting with. Of course, it is... thank you for the question before. Of course, it is a question. It's more economic to deliver your contribution line directly to the head end and connect it. But you have some things to check there on the head end. So you can, on one hand, save costs if you use a direct contribution line to the head end. On the other hand, you have additional cost on the head end side in your configuration and in your setting. And next point would be also a point of risks. Not every program maker can just connect his line with the head end, and there are some points we need to check before. And so normally, yes, for the big multiplexes, we use a site before where they connect their contribution lines, and via that way they goes to the head end.
Okay, that's good. That's great. Additional question from Dr. Riyad Najim. What about latency caused by multiple satellite links? How do you deal with that latency issue?
Yes, yeah, that is a quite complicated issue for us. As I said, we are using two different geolocations for the satellite uplink, and that makes it even more complicated. At the end of the day, it is somehow dealing with timings, and as Hans also described, dealing with settings and the configuration of the delays. Yeah, at the end of the day, at the point of reception, you need to be within the guard interval. And there are coming in a lot of signals, and the receiver needs to get the signal from the transmitter and from the signal that should be. And yeah, we're doing a lot of work to maintain also our SFN networks, which came in via satellite and terrestrial lines.
Okay. Thank you very much, Christian. Yes, we know it can be done because it has been done. So it might be complicated, but it is doable with appropriate attention to detail, let's say. I have one last question for Bernie. I think Bernie's on the line. It is actually from Uday Shrestha. Do you have any workshops or pilot projects on DAB Plus in Nepal? We have people from Nepal on the line. That's fantastic. So we're certainly seeing a bit of a global approach on this webinar, and it's fantastic. It's great. Anyway, over to you, Bernie. What's the answer to the that workshop question?
Well, I think we have our man on the scene, Dr. Les, who is the chair of our Asia Pacific Technical Group. Nepal is and the, you know, that all of Asia, that a part of Asia is definitely on our map, and we've had conversations in the past. So look, we're very interested to hear where you're at in your development of DAB Plus in Nepal, because I think the information we have from our last conversations might be a few years old. But in short, the answer is yes. We usually try and group our workshops in a region, because otherwise it would be an awful lot of travel for us, but we're more than willing to help and support you in where you're at on your DAB Plus journey. And please be in touch directly with the project office, myself and Dr. Les, and we will look into how we can go alongside you on your digitization journey. So thank you for asking.
Thanks, Bernie. And may I add, I'd like to expand the answer. If any country is looking at adopting DAB Plus, talk to us, and we'll do what we can to help you move forward, and help you move forward in the best way possible, most economic, most time efficient, most cost efficient, all of that business. There was another question about availability of these presentations. The presentations are probably already up on the WorldDAB website to get the presentations. The videos will be made available next week, along with the answers to all the Q&A questions. So you can go onto the WorldDAB website and watch this all again. Great. So, and of course, if you want to have direct communication with the presenters, again, go through the project office, and we will connect you together with whoever you want to, and then you can take it from there. So that's great. I think that's all the questions we have. I didn't miss any today. Hopefully. Okay. There was, yeah, okay. I think we're done. So on that, we're a little bit over time. Sorry about that, but hopefully it's been useful. I'd like to now throw back to Bernie, I think, for your closing remarks to this webinar series. This is the end of the line for this year. So Bernie, over to you.
Thanks, Les, and well done, Les, on the excellent moderation that you've done and for the curation of the programme of this webinar series. It's been truly inspirational for me, and I've been in the business for quite a while. The calibre and the care and generosity of the speakers and their presentations. So as we bring this series to a close, I'd like to thank everybody that's participated, not just from the ABU and ASBU regions, but we can see that there are many of you who are from other parts around the world, and maybe closer to us in different parts of Europe as well. So thank you, all of you, for joining and for staying consistently with us over the 3 days. I think that's a testament again to the quality of the material that all our fantastic speakers have shared. And so our thanks again to the speakers, and thank you to ABU and ASBU for their partnership and friendship in making this series possible. You know, we demonstrate through this that the real value of the international cooperation that we enjoy across the broadcast radio industry. So we've heard many inspiring examples and case studies, and we've heard about the challenges in deploying DAB+. And as we've said a couple of times, every country's journey is different, and everybody's at different stages. But one thing we all share is that shared commitment and shared belief in broadcast radio, you know, trusted and resilient, and it allows for these innovative radio services that we can deploy with the technology. So we hope that the presentations have inspired you and given you the confidence to get more involved and to proceed with your journey on digitizing radio in your market. It's reassuring, I think, to know that you have all these experts available to assist you at every step along the way. And to continue the conversation, I'd encourage you to be in touch with the project office. Visit worlddab.org, where you'll find many resources, including the ebook that Dr. Les has written, and also the recently published DAB Plus public policy toolbox. I think that's particularly helpful as well for the countries at different stage of deployment. So once again, thank you to the speakers, to ABU and ASBU for the friendship and the collaboration, and wishing everybody success in their forward journey on deploying DAB+. And we hope to see you again very soon at another DAB+ conference or event. Back to you, Les.
Thank you so much, Bernie. Thank you. And now from ABU, some final remarks from APAC. Over to you, APAC.
Okay, thank you. Thank you all. And first of all, I would like to express my appreciation to Dr. Les Sabel for moderating this comprehensive 3 days workshop. And as always, you have done an excellent job, and we truly appreciate your expertise and professionalism throughout the workshops. And I would like to express my on behalf of ASBU, our gratitude to our partners, WorldDAB and Arab State Broadcasting Union, ASBU, for their excellent collaboration in making this workshop a success. Workshop webinar is a team effort from all the parties in it. And our sincere thanks also go to all our distinguished speakers from day one until today, until end of this workshop, who generously share their expertise, practical experience, and valuable insight over the past 3 days. And last but not least, I would also like to thank all of our participants. Your active participation, thoughtful question, and engagement have made this workshop even more meaningful. We at ABU, we truly delight to have collaborated with WorldDAB and ASBU on this initiative. And I think this workshop has once again demonstrated the importance of international collaboration in advancing broadcasting technology, particularly within the radio ecosystem. Over the past 3 days, we have explored a wide range of topics from our distinguished speakers, Dr. Les and everybody, from progress and policies on day 1 to DAB Plus system on day 2 and network design on day 3. And together from all this session, we have provided a comprehensive overview of the key aspects of the DAB development, and I hope that all the participants have gained valuable knowledge and practical insight that they can bring back to their organization, and maybe take this discussion, maybe from this discussion will provide useful idea and consideration for their future planning and decision making. And once again, thank you to WorldDAB, ASBU, our distinguished speakers, Dr. Les, our moderator, and every participant for your time and engagement and support. We hope to continue this strong partnership, and maybe we can organize more meaningful knowledge sharing initiative. and technical workshop together in the future. I wish you all the best in your future endeavor, and will look forward to welcoming to you again at upcoming ABU technical event. And I just want to promote, if you want to know about more ABU event, you can go to our ABU main webpage, and there is a lot of activity and workshop and we organize there. You can explore in our website. So thank you, and stay safe and have a wonderful days to all. Thank you.
Thank you so much, Shafiq. That's great. That's great. Just remind the audience today that there is a very quick questionnaire at the end of when you close the window and we finish. If you could do that, it'd be great. But for now, I'm going to just say the final word and thank our panelists again. Thank you, Hans Wolter. Thank you, Christian Werner. Thank you, Carsten Sorger, for all your expert input. I think it's absolutely invaluable and really useful for all of the particularly developing countries that we obviously have online today. And finally, thank you, the audience, because without you, it wouldn't be worth it. You're the ones that make it worth it for me. And it's fabulous just to help people move forward. As you've heard, there's many opportunities through the ABU, the ASBU, and of course, WorldDAB, as spoken by Bernie before. We're always here to help. So just let us know and we will do what we can. So for now, I'm going to say goodbye. I hope you have a great day and take away some interesting ideas, and hopefully that will drive some new innovation in your world for your country. So thank you. And for now, bye for now. See you next year. Cheers.
See you next year, Dr. Les. Thank you so much. Thank you all.
Bye-bye.